Good morning, everybody. Thank you. Let me first of all thank the organizers for the opportunity to speak, for the invitation, even if they gave me this slot after the conference dinner. And so thank you for those who came. The title of my talk is Emergence of Kinetic Terms in String Theory. And it's based on these two papers with Jawad Hattab, who is my PhD student. Okay, so let me begin with some quick motivation. Central Swampland constraints relate kinetic terms in low energy effective field theories to towers of massive states in the UV. So for example, the weak gravity conjecture relates the gauge coupling in the theory to the mass scale of an infinite tower of states in the UV. And distance conjecture is also something similar. You can use the kinetic terms for scalar fields to define a field space metric, and then use that metric to measure distances in field space. And when you go to large distances in field space, you get a light tower of states coming from the UV. And these are patterns which seem to be seen universally in string theory, and so they're conjectured to be general, but it would be good to understand better the microscopic physics behind this behavior that we are seeing. And the emergence proposal is one such idea for the microscopic physics, and it says that swampland conjectures are manifestations of emergent kinetic terms for fields in string theory and in quantum gravity. It's something that's been around for a while now, and many people have thought about it in one way or another. So to see what could be the relation between towers of massive states and emergent kinetic terms, it's good to look at a very simple toy model. So we're going to look at the CPN model. Usually it's done in 2 dimensions. We look at it in 4 dimensions here. And in the ultraviolet theory, we just have a theory of n scalar fields. And this is the Lagrangian for it. And it's just like a kinetic term for this complex scalar fields, but with a gauge covariant derivative. But the catch is that the gauge field in this covariant derivative is nothing but some combination of those scalar fields themselves. So in other words, this is a theory just of scalar fields, which is nonlinear. But the interesting thing is the theory has a U1 gauge symmetry, and under this U1 gauge symmetry, this combination of scalars, which we call A mu, transforms like a usual gauge field does. But there is no gauge field in the theory. Now, in the infrared, this theory becomes strongly coupled, and the scalars gap out, except there isn't a full gap because we have this vector combination of them that transforms like a gauge field, and so it's protected from getting a mass. And so in the IR, the only massless modes are just, if you like, in 4 dimensions, would be 2 polarizations of a vector field. And not only that, by RGE running, you also generate a kinetic term for this combination. So in the infrared, you just get a Maxwell theory. So that's an example of an emergent gauge field. There's no gauge field in the fundamental theory, but in the infrared, you get a gauge field. And we would say that these 2 theories are infrared dual. So it's an example of infrared duality between Maxwell theory and this UV theory. And if you look at the gauge coupling of this emergent gauge field, it looks like it's fully generated by the one loop contribution from integrating out the massive states that are dual to the gauge field. So typically, we would have a tree-level contribution coming from the UV kinetic term for the gauge field, plus the one loop contributions from integrating out the states. Because this field is emergent, the whole tree-level gauge coupling is coming from the one loop behavior. Okay, and this is going to be like a smoking gun signature we're going to be looking for an emergent field, or emergent gauge field, that the tree-level kinetic term comes from the one loop integrating out of some massive non-perturbative states from the perspective of the IR theory. And we can already see from here why this could be related to swampland conjectures, because if you want to go to weak coupling, you need large n. So weakly coupled fields mean large number of gauge fields in the IR means large number of massive fields in the UV, and then that translates in string theory to light towers of states. So that's the kind of just toy model, and how is this to be realized in string theory? Well, this is the kind of idea how to realize this thing in string theory. The claim is that any infrared field in string theory is actually infrared dual to some massive tower of states. It's emergent from those states, and this tower, in string theory, you have many towers of states, so this tower is not the lightest tower in the theory. That would typically be like a Kaluza-Klein tower or a string tower, but it begins at some high scale, And the scale where this tower begins is what we call the emergence scale. And eventually what the point is that when you hit this scale, you hit strong coupling in the theory, and therefore there's a dual description. So it's different to the kind of dualities we used to where you move in moduli space and then you change the coupling. Here the coupling running is because of RGE, and in the UV you hit strong coupling and then there's a different description appearing. That's the idea. And then, of course, as I said, if you relate, if this field is really emergent from this UV description, then you automatically get this kind of relationship between the mass scale of this tower and the gauge coupling, which is what the swampland conjectures are capturing. That's the idea. Now, the claim is that this picture is completely general in quantum gravity or in string theory, but in practice, we don't know how to quantitatively really identify this whole structure, but in certain specific settings, we can make some quantitative statements. And that's what I want to talk about in this talk. So how are we going to make concrete quantitative statements? So as I said, the thing we're going to look for is the fact that you integrate out this UV physics, and then the kinetic term you get in the IR, the tree-level kinetic term, comes from the one loop integrating out the UV physics. So we're going to do this integrating out by a background field calculation. So the simplest example is the Euler-Heisenberg Lagrangian. So that's just the Lagrangian for QED after you integrate out the electron. Okay, so how does it look like? Well, there is a kinetic term for the photon because there's a kinetic term for the photon in QED. And then there's all these additional terms in the photon field strength that come from integrating out diagrams like this with the electron running in one loop. And then you can do this integrating out using the Schwinger proper time formalism. That's what you get here, and you get all these different powers in the background field for the photon. Now, if the photon were to be emergent, then what would that mean? It would mean that there would be no tree-level piece at all here, and then the whole of the low energy, the effective action after you've integrated out the electron for the photon would be just coming from this one loop contribution. Okay, that's the kind of analogous thing to what we saw in the CPM model. That's the smoking gun signature we're looking for. So we're going to be looking for situations where the kinetic terms are coming fully from the one loop integrating out of the UV physics, and there is no contribution like this. The setting where we're going to be doing this is in string theory. We're going to consider type 2A string theory on Calabi-Yau manifolds, so compactified to 4 dimensions. And we're going to look at a case where there's just one vector multiplet. And this has a scalar component t. And t is just a parameter that you vary in the theory. You can think of it like that. It's a modulus. And then the analog of the gauge coupling in the Euler-Heisenberg Lagrangian, let's say, is what's called the genus zero prepotential, which controls the two derivative part of the effective theory. And this prepotential always has this kind of universal form. It has this polynomial piece, which you would call the tree-level contribution to the prepotential, to the gauge coupling. In particular, it's dominated by this t-cubed piece. And then it has these exponential contributions that you might call non-perturbative contributions to the prepotential or gauge coupling. And there's also, this controls the two derivative part of the action. There's also higher derivative terms that are controlled by similar type of prepotentials called higher genus prepotentials. They're not going to be so important in this talk, but I need to introduce them because I'll use them in a second. And now what we want to do is so this is, if you like, the analog of the gauge coupling in the low energy effective theory, and we want to integrate out some massive states to see how it relates to this behavior. And the calculation that we're going to do is a background field calculation, like the Euler-Heisenberg Lagrangian, except we're going to give a background here to a graviphoton field. And you integrate out states charged on graviphoton. In this case, they are D2, D0 bound states. And this type of calculation was done in this seminal work by Guberkummer and Waffer in 98. And they showed something like what we were looking for. What they showed is the following. They said, take all these genus G prepotentials, put them all together into this combination, where W is the background graviphoton field strength. That's like the F in the Euler-Heisenberg Lagrangian. And then call this whole thing the all genus prepotential. And now they said, look at the non-perturbative part of that prepotential, the exponential pieces of the prepotential. They said those can be reproduced by a one-loop integrating out Schwinger proper time calculation, just like in the Euler-Heisenberg Lagrangian, except the only difference is now instead of just one electron, you have many charged particles. You have an infinite tower of them, so you have to sum over them. So you have to sum over the wrapping number of the D2, the D0 charge in the D2, D0 bound state, and the genus of the wrap curve. But okay, you have infinite sums here. But the rest of it is pretty much the same. So they said, okay, integrate those guys out. You get a low energy effective Lagrangian for the graviphoton field strength. And then that precisely gives you the non-perturbative parts in the prepotential. Now, when I write this equality here, I put infrared on top of this low energy effective theory that you get from integrating out these charged states. By infrared here, what I mean is that when you do the Schwinger integral, you have to put a UV cutoff on the integral, because it's just like a UV cutoff when you do a loop integral. We don't know how to do the UV completion of it, so they put this cutoff. And so what you actually are calculating is the low energy effective theory after you integrated out the infrared modes of these non-perturbative states. So you haven't integrated out the UV modes of the non-perturbative states because we just cut off the integral. Okay? So in that sense, the non-perturbative part of the p-potential comes from the infrared modes of the non-perturbative states. Now, the emergence proposal says that the full p-potential should arise from this one-loop integral, right? We should recover the whole thing, including the tree-level pieces, from this one-loop integral. But that's not what happened here. And indeed, very interestingly, already the idea of this emergence of moduli space first appeared when the Swampland conjecture, the distance conjecture, was first proposed in this paper of Aguri and Waffer. They said it could be that the infinite distances are generated from integrating out the branes, but then they actually dismissed this idea because they knew already one of the reasons was that in the Gubic and Waffer calculation, if you integrate out the branes, you just get the exponentials, you don't get the tree-level piece. And in this talk, what we propose is evidence that, in fact, the tree-level polynomial piece does arise from integrating out the ultraviolet non-perturbative degrees of freedom, and so just as in you would have it in an emergent field scenario. So what gives? Well, the point is the following. This is the proposal. I told you that the non-perturbative part of the p-potential comes from integrating out the non-perturbative states, but with this UV cutoff. So with the IR mode contribution, now we say let's remove the UV cutoff, integrate to the infinite UV. Okay, so that means you get new contributions to the effective theory. So you get now the full effective Lagrangian, and then our claim is that that will produce the full pre-potential, including the tree-level piece. That's the crucial point. And I should say that this idea that if you remove the UV cutoff in this integral, you will reproduce the tree-level kinetic terms. I think first Isaiah Feiner appeared in this paper, and they do something very different to what we do, but I think the credit should go to them for this idea. Okay, so that's the idea, but of course easier said than done. If you remove the UV cutoff in this integral, you just get infinities, and you get a lot of infinities. First of all, you get an infinity from there's a pole in 1 over s, from s equals 0. It actually goes like 1 over s cubed. So that's infinities. And then you get a second infinity from the fact there's an infinite sum here, and this infinite sum is typically regulated by this exponential, but when s is 0, you don't have this regulation, so you have an infinite sum over infinite terms. If you just set epsilon to 0, so we don't know what to do. And secondly, you shouldn't even be allowed to set epsilon to 0. Why? Because we're integrating out that branes, and we're treating them like particles, running doing a Schwinger loop calculation for them. And that's okay as long as the modes you're integrating out are much bigger than the brane itself. But if you want to integrate to the full UV, you have to integrate that distance scale smaller than the size of the brane, and so it makes no sense to even treat it like a particle anymore. You will need to somehow quantize the brane and integrate it out then. So this seems like challenging to remove this UV cutoff, but there we're going to propose 2 ways to regulate this UV, to understand this UV cutoff, and show that indeed this proposal is we believe is correct. And the first piece of evidence is the following. And you can just look at a simple example. So you can look at a resolved conical, which is just a non-compact cone with a 2-sphere in the at the origin. Of some size, and the genus 0 pre-potential then takes this canonical form. There is this polynomial piece, and then there are these exponential corrections that appear in this trilogarithm. And now, Gubic-Waffer calculation tells us how to recover this exponential piece. You just integrate out the d2, d0 states here. In this case, there is just a single d2 state and the sum over d0 bound states of it. So there's just the sum over n, that's the d0 charge. It's an infinite sum. And then you just do this integral, and you get this tri-logarithm. Okay, so now how do we UV complete this integral? So what we say is the following. You can rewrite this as follows. You resum the integrals over all the d0 states you do Poisson resummation, and then you get a sum over infinite number of Schwinger integrals with delta functions that are localized at integer values of the Schwinger proper time. And what you then do is take this infinite sum of Schwinger integrals for each of those localized Schwinger proper time, and you write them as a single complex integral. So you analytically continue the Schwinger proper time, And what you do is, since these are localized at integer values Schwinger proper time, then you just have a function with poles at integer values of s. That's the Schwinger proper time along the real axis. And then each one of these poles will give you the contribution from each one of these integrals. So then you just take a contour like this, and this will reproduce for you the sum of all these integrals. But now if you want to remove the epsilon cutoff, you want to set epsilon to 0, so you want to include the 0 Schwinger proper time contribution, then that just corresponds to the pole at the origin. Now importantly, this pole at the origin is not the UV contribution from any one of those particle integrals, but it's the UV contribution from the whole infinite tower. Okay, so only after you resum the whole tower, you resum the tower, can this pole give you the UV contribution. And now, to include the UV contribution, you just have to include in the contour the 0 pole, and the answer you get is no longer infinite, you get something finite, and in fact you get precisely on the dot the tree-level piece of the pre-potential. So our interpretation of this is just a statement that, indeed, if you integrate out the non-perturbative states, but now you integrate to the full UV, you don't cut the integral off, you recover the full pre-potential, including the tree-level kinetic terms. And as I said, if you, through one loop calculation, recover the tree-level kinetic term precisely, so there is no other contribution, that is evidence that that field must be emergent. That's the idea. And so this is the first piece of evidence that, for the emergence statement. Now, can we see this integrating out even more directly? We claim the answer is yes, but as I said, since you're integrating out scales much smaller than the brains, you have to resolve the brain into its constituents in some sense, and then integrate out that constituent. And it turns out that in certain type theory background that can be done, and the way you do that is you exchange your expansion of G string for an expansion in 1 over G string, and then those 2A backgrounds are known to have a certain description as a Fermi gas in this beautiful work. And what does that mean? Let's see what that means. So the prototypical example is the blown up conical, which is just a cone over 2 spheres, P1 times P1. And then what is known as the following statement, that the all genus fully non-perturbative pre-potential, this F, is matched precisely onto the grand canonical potential that's associated to a single particle Hamiltonian of a free Fermi gas of a one-dimensional fermion in an external potential. So one-dimensional means one space dimension, since it's a quantum mechanics here. And the relation is just the following. G string is related to H bar in this system, as I talked before. And then T, the modulus parameter, is related to the chemical potential of this fermion. And this is precisely the map. And then if you relate those two this way, you find that the full pre-potential is given by this grand canonical potential. Now, the reason this formalism is very interesting and powerful is that this allows you to calculate non-perturbative corrections to the pre-potential, and that's why people are interested in it. But we're interested in a much more mundane question, just how to get the tree-level kinetic term and the tree-level piece, the TQ piece, and that, of course, is included in this pre-potential. Now, how do we understand this relation here from the picture of emergence that I just told you about? Our claim is that this is nothing but an integrating out calculation, just like Guber-Kummer-Waffer. We integrate out the UV modes, and we get the full pre-potential low energies. So this is a toy model to illustrate why we believe that's true. So what we do is we take this fermion, and instead of treating it like a quantum mechanics, we promote it to a field. So now it's a two-dimensional fermion, so there's also time, on S1 times R, so it's a second quantized fermion. And then, so you take this two-dimensional fermionic theory, you put it at every point in four-dimensional space-time, and you couple this fermion to a background gauge field along the time direction, the Euclidean time direction. That's what a chemical potential is in the second quantized theory, in the quantum field theory. And now we just integrate it out in the path integral. We can do that, it's a quadratic theory. If you integrate it in path integral, what do you get? You get an effective action for the chemical potential. So you've just integrated out this fermion, and you get an effective action for this chemical potential. What is that effective action? It's nothing but the grand canonical potential of the one particle Hamiltonian of this fermion. So that explains to us what this J is. It's just the effective action for the chemical potential after you've integrated out this fermionic field. And so our claim is this is a toy model showing that this calculation of the Fermi gas is nothing but a Guber-Kummer-Waffer calculation. The only difference is that in Guber-Kummer-Waffer they take the string coupling to infinity and send the graviphoton field to 0 at the same time, so that you have a genus expansion in the pre-potential. And this calculation is at finite graviphoton, so you can set it to 1. You no longer have a good genus expansion, but you have an expansion in this H bar, which is 1 over G string. So as I said, if you integrate out the fermion as a two-dimensional field, the effective theory you get for the chemical potential, which is mapped to the scalar modulus, is nothing but a grand canonical potential, which is nothing but the pre-potential, including the tree-level piece, including the cubic kinetic terms. And so again, we just recover the same thing, that integrated out the UV. At one loop, you recover the tree-level kinetic terms for the theory, except here we understand it much more microscopically. And the D2, D0 states of the Gruber-Kommer-Waffe calculation in this fermionic picture are solitonic states from this perspective. Okay, so this has all so far been in non-compact settings. So these are non-compact cones with some base over some base in the middle. Can this work for a compact setting where you have dynamical gravity? We claim the answer is yes. You can consider the following: just take an elliptic fibration over a toric base, and the toric base is specified by some toric vectors VA, and then the elliptic fiber, the torus size, is given by some modulus T, and then we're going to try to recover the T cubed piece, the tree-level kinetic term for this size of this torus, from integrating out this fermion model. So this is the Hamiltonian you should write down for this fermion. It's just given by, so there's Q, that's along the space direction, and there's a momentum P, and then the combination is given by these toric vectors, and this is nothing but the spectral curve, for those who know these things, associated to this base for the case of a cone. But the point is that if you integrate out this Hamiltonian, you generate the correct T cubed piece for the size of this torus that you can show. So the Q piece is given by this, like this. Now, we're not claiming this Hamiltonian will give you also the non-perturbative parts of the pre-potential, or even the and maybe it does give you the subleading piece, but I don't know about non-perturbative pieces for sure. What we're saying is this Hamiltonian is capturing the large chemical potential, high energy behavior of whatever the UV system is in this compact setting, and those modes, which are the ones responsible for the cubic terms, are captured by this Hamiltonian. And that's why it gives us the correct intersection number, the correct cubic term for this size of this torus. And what we propose is something even more general. We say that take any compact one-parameter Calabi-Yau, and then what you should do is you should identify the period, the so-called D6 period, as the grand canonical potential of the UV system, whatever that UV system is. It could be a free fermion, it could be something else. So for example, if you take this Calabi-Yau here, there is a one-parameter modulus, the complex structure modulus, or the mirror, which is a Kähler modulus. You identify this with the chemical potential of the UV system. And then the period has this Mellin-Barnes integral representation. You identify that with the grand canonical potential, the classical grand canonical potential. And as I said, when you have these Mellin-Barnes integral representations, we should really think of them as analytically continued Schwinger integrals. So this is just, you see explicitly, this is just integrating out the UV physics, which is precisely what the grand canonical potential is. If you integrate out a field, you get the grand canonical potential as the effective action for this chemical potential. And then you just need to map this chemical potential to the modulus T, and you recover the tree-level kinetic terms, the cubic pieces. To summarize, we argue that tree-level kinetic terms in type 2A string theory determined by the cubic pre-potential should be thought of as emergent from integrating out non-perturbative states, and this we claim is a smoking gun signature that the whole field is emergent, since its tree-level kinetic term is coming out just purely from one-loop physics. We propose how to do this calculation, how to UV complete the Schrödinger integral by an analytic continuation, and then we gave an even more microscopic understanding of this UV behavior through a strong couple of Fermi gas description. And we said that the pre-potential should just be understood as integrating out second quantized two-dimensional fermion. Now, I should say this fact that this is a toy model, we promoted the fermion to a field is highly non-trivial because in this Fermi gas description, the fermion number through a geometric transition is mapped to the number of branes wrapping the cycle in the geometric transition. And so if you're promoting it to a field, then it's like a field for the branes. So we've heard about string field theory, but it'll be like a field for a brane field theory. And then you integrate out this brane field in the path integral. That's what this toy model is supposed to be capturing. And if you do that, though, you generate the emergent kinetic terms. That's our claim. And we began applying these ideas to compact cases with dynamical gravity. Now, the claim is that this emergence story is completely general. But as I say, many open questions remain about how to realize this idea in other string theory settings. This is, in some sense, the first setting where we can really make some quantitative statements. Thank you.
Thank you very much, Eran, for a great talk, and that's perfect timing. Any questions? Please.
Thanks for the talk. So how should one think about integrating out in a context where space-time emerges together with fields?
Right. So that's why this is the time, when we did integrating out, we just took a two-dimensional fermion, coupled it to a background field with chemical potential, we integrated out in a path integral. This is fairly standard calculation. As I say, what it should really be capturing is some kind of brain field integrating out in a path integral, and it's likely that space-time would emerge at the same time as the kinetic terms here. So this is capturing just some aspect of the full story.
Right.
Yeah.
Thanks.
I don't know how to do the full story. Yeah.
Can this be understood as in the context of the duality between matrix models and, let's say, topological strings or something?
That's where this Fermi gas description comes from. So you just take topological strings on this background, and then that has a matrix model description. And then the matrix model, that's what's shown in the paper by Marino, that this matrix model can be described as a fermion, a one-dimensional fermion. So this comes from a matrix model. That's why you can get the full non-perturbative pre-potential, because it's described by this matrix model. Yeah.
In the matrix model discussion, what is this emergent kinetic term that you are talking about? Is that part of the curve that describes the...
Well, the matrix model gives you the pre-potential, and that includes the tree-level piece, T-cubed piece. So that's all I can say, yeah.
Question?
So in your deformation of the argument, you express this poled origin through the discontinuity. And so when you do this deformation, it includes the arc at infinity. What is the fit? So when you deform the contour, you drop the arc at infinity, right?
You mean in this infinite sum? I don't deform the contour, I just include the, or I mean, if you integrate just over the origin, you just get this piece. But if you integrate over everything, you get the whole pre-potential. So if you just extend this like this, then you will get the whole pre-potential.
Okay, but so...
I'm not moving this contour over here, if that's, yeah. Does that answer the question? Or?
It looks like sometimes, you know, if I take a graviton scattering, the kinetic term of graviton, in a sense, comes from the UV, but it comes from dispersion relations. And so I was trying to understand if this is, again, you're just proposing a dispersion relation. But then we always worry about the contour at infinity, which corresponds to the Regge limit. And I was wondering, what is the physics of the large arc here?
I do not know. It's a good question. I don't know what the meaning of this analytic continuation of the Schwinger proper time, but mathematically this representation has been known a long time. It's like a Mellin-Barnes integral representation. Physically, I don't know what it means.
Okay. Kumran?
Very nice talk, Eran. I'm up here.
Okay.
So, yeah, indeed, you have presented very convincing evidence that local models, when you integrate out the non-perturbative states, when you regulate the epsilon, you could produce a cubic term. However, this is additional contribution on top of whatever there is. And the main problem we had with Hiroshi was that cases where that term doesn't even exist, for example, in the case of T6, where there is no non-perturbative contribution by supersymmetry, there is still a T-cubed piece. And that T-cubed piece cannot come from any integrating out because it's by supersymmetry, there's no correction. That was our major problem. I don't see how this solves it.
Thank you very much. From up there. First of all, let me just comment about the first thing you said. When you do, the whole point is that when you integrate out, because we can do it precisely, you get exactly the coefficient of the cubic piece. So there is nothing else there. It gives you the full thing.
No, the conifold is ambiguous, actually. For the conifold, this is a contribution to cubic piece.
You can also do it for elliptic fibration. You get it precisely the coefficient. There is nothing, there's no room for anything else. That's the whole point, that it comes purely from this.
Well, to avoid the ambiguities of the sort you're saying, if you go to T6 case, there's absolutely no ambiguity. There is no contribution because it's zero, the integral.
Right, so as I say at the end, sorry, I need to go forward. As I say at the end, I do not know how to realize this precisely in all string theory settings. Including higher supersymmetry settings. But there's a reason for that, because if you have other settings where you have like a torus, it looks like the simplest setting, but it's not the simplest setting, because there are many possible states that you would need to integrate out. What you want to do is project is to go to a situation where you have control over the states that you need to integrate out, the most control. So these are like supersymmetric settings. So for example, this is really a torus. So we reproduce the kinetic term for this torus, the size of the torus, except we don't take a torus over just a torus, but we have to take the torus over a toric base. And this projects out, because you see, if you want to reproduce the high dimensional Vichy scalar, that reproduces all the possible lower dimensional geometries. But what we do here is we fix the lower dimensional geometry and we just reproduce one specific mode. So one particular component of the high dimensional Vichy scalar, and that's a much easier calculation. A bit like in the BFSS model where you reproduce one particular contribution from the Vichy scalar to the 2 graviton. We don't know how to reproduce everything. That's all we're saying, yeah.
Okay, so let's thank Eran again.